everyone, have a good session. We start in 5, 4, 3. Over to you, Samriddhi.
Yeah.
Take it.
Good evening, everyone. And on behalf of the ICTS, welcome to another exciting event organized by Cosmic Zoom. I'm sure most of you know about Cosmic Zoom. So this is this wonderful virtual exhibition, a celebration of science, which features talks, which you'll find on our YouTube page, and the links are there as well. Apart from that, there are also many virtual guided tours, and you could look up the website and sort of figure out how you want to engage with all the wonderful stuff that's happening in this sort of virtual exhibition. As I said, this sort of exhibition also involves these talks that we are having in the evening. And today we will hear all about clouds. And it's a talk which will be given by Professor Rama Govindarajan. It's actually, for me, it's a really great pleasure to introduce my colleague, mentor and friend, Professor Rama Govindarajan. And that's because, you know, for all of us who know and admire Rama, she's not one to stand on ceremony. So I will introduce her a bit differently in keeping with the spirit of this exhibition. So Rama is a scientist in the classical mode. By that, what I mean is that she's one of those very rare individuals who wanders effortlessly across areas of engineering, physics, applied maths, meteorology, climate science in a way, you know, very few can. And if one were to put a label, then it's really fluid dynamics, which is the sort of central glue which binds many of her walks together. She's been a champion in the studies of flow instabilities, what pushes laminar flows to go unstable. She's done marvelous work in the areas of vortex dynamics, entrainment, turbulence, of course, as well as the dynamics of all sorts of objects when they're transported in a flow. This is, of course, apart from her interest in the microphysics of clouds, of which we will hear today. So, you know, what I want to talk about is that the originality, impact, and depth of Rama's work, of course, has received recognition from across the world, including India's highest awards, the Bhatnagar Award, fellowships to several academies and elsewhere. So I won't go through that laundry list. What I want to emphasize is a feature of Rama's work which makes her sort of unique and me certainly envious. And this is her ability to make remarkably difficult concepts sort of accessible to a very wide cross-section of people, you know, from young students to professional scientists, everyone. And this really comes from years and years of really hard grind, thinking of things deeply, and perhaps, and Rama will correct me on this, perhaps even obsessively to sort of internalize ideas in the way she does. So in this talk, you will see evidence of this, and I'm sure there will be many sort of aha moments, because behind all of this is curiosity. And Rama is a person who is curious about everything, not only stuff which we as professional scientists are sort of taught to be curious, but, you know, just everyday phenomenon. And which is one of the things which I suspect makes her an absolute favorite with her students. And the reason I'm saying this is essentially to encourage all of you to ask as many questions as you would like to have. Rama will be more than happy to answer all of them, because Rama sort of loves working with young people, because, you know, she retains that same sort of infectious enthusiasm that I imagine must have propelled her to a career in science all those years back. It's a trait that she encourages in all of us, including her many, many students who've had the privilege sort of to work with Rama. So today, Rama, we will share her enthusiasm for what makes clouds tick. So with that, over to Rama.
Thank you, Samriddhi. That was like too kind an invitation. Introduction. I'm now scared to give this talk, but let's go ahead. You don't yet see my screen, right?
Not yet, Rama. Now, yes.
Now, yes. Okay.
It works. Perfect.
Okay. Okay, so the title of today's talk was Cloudy and Turbulent Days and the Wait for Rain. So today we're going to talk about, many of the things we normally consider as bad things, like cloudy is usually, connected to, my future is cloudy, my life is clouding up. You see it in, negative context very often, but today we will say that in sunny versus cloudy, cloudy can be good. Like that's important. I mean, that's not something I need to convince you guys on, because monsoon clouds are very important to us in India, and that we all know. But I'd also like to convince you that in the thing of turbulent versus calm, turbulent can be good. Normally we face turbulence. Actually, when we fly through clouds, we face turbulence. So when your plane goes through something like this, your pilot is going to say, put on your seat belts, and then you're going to wish and wish and wish that you come out of this big cloud thing very quickly. So you think of turbulence as a bad thing, but we're going to show that turbulence is a very essential thing. That's one of the things we're going to talk about today. And then when we say rainy day, it's usually in a negative context, but we're going to, the people who wait for monsoon, for them, rainy day is a positive thing. The last thing, the last bad thing, which we're going to call good now, rename as good now, is aerosols. So normally we think of aerosols as, these awful, terrible dust and, some effluent particles from industry, which, dirty up the whole atmosphere. We're going to see that aerosols are very essential for, rain to happen. So we will see that also in today's talk. Okay. Okay, so let's talk about the ABC of cloud formation, which all of us know from, I don't know, primary or middle school. So like there's, some, layer of water on the earth. It could be an ocean, it could be a lake, or even some wet mud. And then because the sun shines, this water is going to evaporate. Now, when the water evaporates, this little blob of evaporated air that I've represented here is actually moist because it contains a lot of water vapor, and it is typically warmer than its surroundings. And so it's lighter than its surroundings. Water vapor is lighter than air, and if it's warmer, it's going to be lighter than the surrounding air. And because it's lighter, it keeps rising. It's like, a bubble rising through, water that you're trying to boil. So it keeps rising, rising, rising. And at some point, it reaches this height where that the temperature in the Earth's atmosphere keeps going down as we climb up. So like typically we talked about planes flying. So where a plane flies at 10 kilometers or something, the outside temperature is like minus 40 degrees. So well before it reaches 10 kilometers, this amount of moist air, the water vapor that's being carried up, up and up, is going to start condensing. So now, like we know that, when we keep something in the fridge, then water vapor condenses. Like even if you keep a dry plate in a fridge, you will see condensation taking place on it. So if we cool any blob of moist air, it's going to condense out. And that is what is happening in a cloud. Like basically, because you cooled it by the atmospheric temperature itself going down, you are going to start condensing. And when you start condensing, you see a white thing or a black thing. So from here, you see this white or black blob from the ground. And that is basically tiny little droplets of water, liquid water that you're seeing. So, one question that you may ask is, why doesn't the cloud fall down? Like liquid water is 1,000 times heavier than air. So all liquid water should be falling down. Actually, it's true, like clouds are very slowly falling, but these drops are so small that the terminal velocity is kind of small. Now, I put all these little blue dots. Each of them is formed on an aerosol particle. And we will come to that in the next slide. So, one second. I'm trying to reduce the thing on the side so that I can see my screen. Okay, so let's talk a little bit more in detail about cloud formation. We said the temperature in the atmosphere keeps falling down with height, down, down, and down with height. And so the amount of moisture that this guy is carrying has a certain relative humidity at a high temperature. You know that it's going to get saturated very soon. So the relative humidity of this blob, if it doesn't mix with the environment, is going to go higher, higher, higher until it reaches a line called a lifting condensation level, where the amount of water vapor that this puff is carrying is going to become saturated and you start condensing out. So when you condense out, condensation cannot happen out of nowhere. And this is where cloud condensation nuclei or these aerosol particles come in. So if you're slightly above supersaturation, you are going to condense only onto a surface. Just like we talked about the refrigerator, we said that, if you have a plate, a dry plate, then droplets form on it. Droplets need like liquid surface or a solid surface to form on. They can't form right in the middle of air unless you are 700% supersaturated. If you're 700% supersaturated, then spontaneous liquid drops can appear out of nowhere. Whereas if you're just 1 or 2% above supersaturation, in a cloud, it's never above 5% supersaturated. You need these particles to hang the droplets on. The droplets need this crutch to form on. So aerosols are a crucial ingredient of clouds. Okay, so what does a cloud fluid contain? A cloud fluid is mainly air. It has some water vapor as we discussed, but a vast proportion of cloud fluid is just air. It has some water vapor. It has temperature variations within it, as we discussed and we will discuss. It has a suspension of aerosol and of tiny water droplets also. So all of these together go to make a cloud. The water droplets are in very dilute suspension. It looks like, not at all transparent. When you see it from below, you see a thick white mass, but actually it's very, very, very dilute. It's just that because it's so thick, like the cloud is so tall that, the optical, it becomes opaque. So, but it's dilute. So now we want to understand the fluid dynamics of this cloud. And in general, like dynamics is how fluid flows in response to applied forces. So you apply a force and you ask how it flows. And this is basically Newton's laws that we will talk about a lot. So I want to bring in this word turbulent here. I already said it's a good thing. A vast majority of flows, let's say it's chimney smoke, it's, effluent coming out of a volcano, it is when you drive a car, it's the effluent that you're putting out. Any such example, a vast majority of these fast flowing and large length scale things are turbulent, and clouds are just one example. So any flow that's big and moving fast is going to be turbulent. That we can take as a pretty decent thumb rule. So like all these things are turbulent and clouds are also turbulent. We'll say more on that. Small scale and slow flows are typically laminar. So Shamriddhi had introduced this term laminar. This is the opposite of turbulent. Like when you open your tap slightly in your sink, you will see a clear, thin stream of water coming down. And that is usually a laminar flow where each molecule of water, not molecule, each little blob of water is actually moving downwards with a known velocity and doing nothing very surprising. So these flows are laminar. Now, in clouds, you get laminar type behavior as well as turbulent type behavior. The laminar type behavior happens very close to the small droplets. So when you look at a small droplet, it's almost following the flow. So the velocity difference between it and the surrounding fluid is very, very small. And also its size is very, very small. So then this quantity called the Reynolds number. we will use this. We may need to use this again. So it's a thing which is a good thing to fix in your mind. There's a velocity, typical length scale, and what is called a kinematic viscosity in the denominator. This number has no dimensions. And for when velocity and length scales are small, then the Reynolds number is small and the flow is likely to be laminar. When these two are big, the Reynolds number is big and the flow is likely to be turbulent. In clouds, the Reynolds number is like, tens of millions. So it's very, very big. So it's very, very turbulent. So now we discussed about the formation of clouds. I'll show you a simulation of Ravichandran and Narasimha. They did it with this brilliant code called Megha 5, where Megha stands for cloud, of course. So like here is the movie. Let me stop it for 1 second. Yeah, what we're going to see is in this panel, we're going to see the upward velocity U. In this panel, we're going to see what is called the potential temperature. We can think of it as a temperature difference. Basically, we're going to see a temperature difference between the cloud and the surroundings. And in this frame, we are going to see liquid water. So this is just to fix in your mind what we've been talking about clouds. So like here is a warm patch which is rising. See, it's warm. You can see that the temperature is higher than the surroundings. The difference in temperature is very, very small, okay? But still it rises because it's lighter. So here is a warm patch which has an upward velocity and it's going to go up, up and up. It will reach some height and start condensing out. So that's when you'll see liquid water. So let's watch this movie. And this is happening every day when clouds form, except you don't see what's happening near the ground. You see only this thing after it's reached there. So you see that some warm air is moving up, up and up, like there's evaporation going on or whatever is going on. And you see the first cloud formation. This is actually cloud formation that you're seeing from this rising bunch of wet air. So Megha is a beautiful simulation code which can do all this. So you see that the cloud air is slightly warmer than its surroundings. And when it's red, that means lots of liquid is formed. It doesn't mean the cloud is red. You'll see like it to be whiter or maybe even gray depending on the optical depth.
Rama, can I just interject with a quick question from one of the members of the audience?
Sure.
So the person wanted to know, in your Reynolds number definition, what are those letters U, L, and nu? I suspect not V. Yeah.
Okay. So U is a velocity scale. We choose a typical velocity. So in clouds, you may choose the upward moving velocity of the jet itself, or you may see like if there's a big vortex, what is the speed at which that vortex is moving. So you can define it in many ways and it's a typical velocity. L is a typical size scale. Like if the cloud is 100 meters wide or a kilometer wide, L is a typical length scale of the cloud. So now like when both of us look at a cloud, I may choose some other U and you may choose some other U. I may choose some other L and you may choose some other L. So our Reynolds numbers could be very different from each other's, but we can always scale into each other's Reynolds numbers. So first thing about a Reynolds number is it's not universal. It depends on the user. Like the user can define it in any way he or she likes. And nu is this thing called the kinematic viscosity, which is basically the regular viscosity divided by the density of, in this case, it's the density of air. So it's the viscosity of the fluid divided by the density of the fluid. And this you can see is meter per second. This is meter. So this is meter square per second. Nu is also in meter square per second. And when you divide one by the other, you get a dimensionless number. Typically, when it's high, you can expect flows to be turbulent. So is this the question that the person was asking? Does it answer?
Yes, I think so. Yes, Rama. Sorry.
Okay. Any other questions?
Not for your immediate thing. There are a bunch of them, which I think can be done at the end of the talk.
Okay. Okay, so I said that any flows are turbulent. So I'm actually going to depart a little from clouds and talk about turbulence, so that when we talk about turbulence in cloud, we can appreciate, where turbulence comes in and why it's a good thing, why it's important, and all of that. So this is a recent volcanic eruption of the volcano Shinmoi Dake. And you see, I mean, I don't have to tell you that this flow is turbulent. Here is just a, terrible, accident on the sea surface where something is burning and there's a hot plume which is rising. And here is blood flowing through a mechanical heart. But even in our big arteries like our aorta and all, the blood flow itself is turbulent. So there's lot of interesting dynamics going on in this turbulence. You can see that there's some structure here, and we will talk about it in more detail as we go on. So turbulence is chaotic and random. Everybody thinks of turbulence as chaotic and random. But here I want to differentiate between the mamul, normal chaos and random motion, and turbulence. So turbulence is not white noise. Turbulence is not some random jitter. It's highly space and time correlated. And this is the one thing I want you to carry back home, even if, you forgotten the rest of the lecture. Remember that turbulence is highly space and time correlated. So here you see this. It's nothing except, if you take a table, so you have a table at home, you're the desk on which you study, you put on a table fan at one end. So just switch on a table fan at one end. And that's all you do. If you could see the air, this is what you would see. If you could see what the air is doing. And here what the person who's studying this flow has done is that they've taken this quantity called the vorticity, which is the curl of the velocity vector, del cross u of the velocity vector. Now, don't worry if you don't know what a curl is or whatever, it doesn't actually matter. It's basically a measure of how much rotational the flow is, how rotational the flow is. So whenever you see this red, it means there the flow is very rotational. And whenever you see blue, that means it's not very rotational. So you see that instead of random arrangement or random running around of various air parcels in, random ways, it's actually arranged in nice vertical patterns. And the vorticity, if you see on my table, they all look like hairpins or horseshoes. So they have particular shape, okay? So this rotational thing is arranged itself in a kind of shape, and there's many of them. They're all random. They will be born whenever they like and die very often. So each of them is not going to remain for too long. It's very time dependent. But one very important aspect of this vortex is that each vortex can have an influence on all the other vorticity and all the other flow. So it can, make other fluid parcels move in obedience to what it wants. And similarly, this one will respond to others. So they all keep influencing each other. And it's a very horrendous mess, very difficult to calculate, as we are going to talk about. So I just want you to take away this impression that there is some pattern in most turbulence. And so if I take a very small portion of a cloud, extremely small portion of a cloud, remember clouds are turbulent, they contain water vapor, droplets, and aerosol particles. This is what you're going to see in vorticity. This is an actual simulation. And you see, like, this is how. So things are arranged in tubes, like almost pasta noodle things. And depending on how fast they're rotating, you color them differently. So these are the pasta noodles. They're all of different radius, length, everything. They're all of very different scales, length scales, and even their lifetimes are very different. And so imagine a big bowl of pasta, except that the pasta is all alive, like almost. They're all rotating, they're telling each other how to rotate, and they're born, they die, they do all of this. So this is what is happening inside the cloud. So no wonder your poor little airplane gets thrown around when it, goes through this. Like, there's this frenzied rotational motion going on. So if only we could see rotationality, this is exactly what we would see in a cloud. So like a vortex, just a cylinder which is rotating, can be thought of as a building block of turbulence. Oops. So did my screen go away?
Yes.
That came
It's
back.
back. It's back.
Okay. So this is basically, the only thing I can tell you about turbulence in this talk. So we've agreed that this cloud flow is turbulent, like this chimney smoke is turbulent. There's another mystery which I will only talk in this slide, and you can ponder about it. Even I don't know the answer, and most people don't know the answer. Probably no one knows the answer, but I'll raise the question. So here is a chimney, and here is smoke coming out of a chimney. Now, very, very close to the chimney, you see the smoke very clearly. You see this white, messy thing. You can see it's turbulent, like you can see vorticity and stuff like that. You go a certain distance away, it's become lighter. You go an even more distance away, it's even lighter. You go even further away, there is no smoke. It's all gone. So what is happening? What is happening is this thing called entrainment, where suppose you have a jet climbing like this, outside air is being dragged along. Outside air, which used to stay calm and not moving, is dragged along with this jet. So then when this jet drags outside air, it shares its own momentum with all the outside air. It also shares its own soot particles or whatever, water vapor, whatever it's carrying. It shares with all the new neighbors, and they all start moving very much more slowly, because like the momentum is shared across many a big region now compared to what it started with. And so it starts moving slowly, and these soot particles or whatever are shared among so many air parcels that you see that you don't even see it after a while. So it becomes so dilute. So entrainment results in dilution, slowing down, and in the case of a cloud, it gives opportunity for evaporation. So suppose I'm climbing up with some droplets, and then I have like some water vapor, and the water vapor, so the surroundings are so wet that the droplets are not drying. You know that on a rainy day, our clothes don't dry. So if there's lots of water vapor in the atmosphere, these droplets will not dry. But suppose the droplets are climbing through, air, which is dry air being sucked inside. This dry air is going to act like a fan, and it's going to dry out these droplets. So the mystery is, like, when a chimney smoke dies off, it doesn't reach the stratosphere or something like that. It dies off pretty fast. How does a cloud go up and up and up for so many kilometers? Especially our monsoon clouds, cumulonimbus, they go all the way to the stratosphere. So, like, first of all, how do they reach that height? And how do they form at all, and how do they keep rising? So these vortices on the edge of the cloud, you can see these vortices, they should be dragging in outside air, and the cloud should be killing itself by sharing its water vapor with everybody and sharing its warmth with everybody. So it's not lighter and no momentum and nothing. So this is a mystery. Why do clouds form? And I cannot give you the answer to this. Okay, so now let's talk about droplet growth. We've assumed that the cloud is in this mysterious way reach the top. So the mystery is, the one answer to that mystery is that entrainment is practically shut off or reduced a lot in a cloud. So it doesn't grab dry air the way other jets, other turbulent flows do. So what is different? That I will not address today. But when it's reached the top, I said that, oh, like there are these aerosol particles, and then droplets start condensing onto the aerosol particles. But that's not the whole story, because so like here is a droplet which is growing, okay, and it's surrounded by water vapor. It's now in a place in the cloud where the temperature is pretty cold, so condensation can happen on it and its radius can grow. But as its radius grows, the water vapor gets depleted in its surroundings. And then, like, the temperature in the surroundings rises due to latent heat. So once the temperature rises, it's harder to condense. And once the water vapor is depleted, it's harder to condense. So then it grows very, very quickly to some 10 microns. Actually, you can do this calculation at home with just 12th standard knowledge. So in very, very short time, an aerosol particle which was 1 micron starts becoming 10 micron or 20 micron. But after that, like, the growth is completely shut off. Even without the temperature change, even without everything, the growth is actually practically shut off. So it can reach something like 10 microns in 30 seconds. But after that, it basically doesn't ever grow. It's reached 40 micron, and after this it's going to stay 40 or 50 micron for hours and days, and it's never going to grow to a raindrop. We agree that a raindrop has a couple of millimeters dia. So like these condensation is not going to do the job. Condensation is not going to create rain. So this is the message in this slide, which I call droplet growth bottleneck. So like there is this mystery about droplet growth, and the part 1 of the story is that condensation is not going to make rain. It's not going to alone make rain by a long shot. You can get 40 micron droplets, but not raindrops. Okay, the other part of the story is gravity. So like one thing that you can say, I mean, you can come up with some thought is, here is a big drop and here are many tiny drops. And we know that the terminal velocity of the big drop, again, you can calculate its terminal velocity based on, Stokes' flow that you've studied in high school. So there's a big drop which is falling, and there are smaller drops. The big drop falls faster than the smaller drops. So as it falls, it can collect all the small drops in its in the region just below it. Because it's falling faster, it can catch up with them and collect them, and it can grow by coalescence. It can grow by uniting with all these little drops. But remember, if I have a 10 micron drop or a 20 micron drop, which is what I could achieve by condensation, a million such drops should unite together to make a 1 millimeter raindrop. And like gravity and this difference between these small particles is never enough to explain that how a million can unite. Okay, so the reason is that a cloud itself lives for an hour or so, and if it is going to take weeks and days for droplets to form, then the cloud would have died by then, so there'll be no rain. So the second part of this story is that gravitational coalescence or gravitational collection and growth, and this is a formula which you can derive at home if you like. Just write down the terminal velocity of this one, see who all it will collide with. In the simple way we do kinetic theory of gases, we ask how molecules collide, what's the mean free path. You can ask such things about falling droplets and come up with this formula on your own. And you will see that already if you have a bunch of 100 micron droplets, then you can explain growth to a millimeter by a few minutes. But if you don't have 100 micron droplets, remember in the previous slide, we did not have any 100 micron droplets. These are all, log scale. After many hours also, we did not have them. So like where can gravity start acting? So gravity cannot, be the story of what causes rain. So what causes rain? Let's first see one more picture on gravity. Basically, I'll run very quickly through this picture because I'm running out of time, but it just makes the point very firmly that gravity cannot, even if there's perfect coalescence and even if there are droplets everywhere, then it can never, make a 1 millimeter drop for many, many seconds, even if you start out with a big one. So, and you don't have droplets everywhere in the Earth's atmosphere. Below every cloud, there's dryness, and so you're not going to have that. In fact, below the cloud, you're going to have the droplet shrinking away due to evaporation. So the tiny droplets are actually going to evaporate before they reach the ground. So it's only the big droplets which fall so fast that they can reach the ground before they evaporate. So you already need like millimeter sized droplets to reach the ground. So this gravity, this thing is not yet telling the story. So there is this thing called bumblebee logic. So basically, when I was a student of aerospace engineering, and when you reach the aerospace engineering class, you're told that if you're a good aerodynamics person, you know that a bumblebee cannot fly. You know all the rules of flight, and you know that a bumblebee cannot fly. And so the only lucky part is the bumblebee doesn't know this, so it defies logic and flies. So by that logic, by any simple thought process that we could come up with so far, we've come up with the concept that there should be no rain. Enter turbulence. Turbulence is a very, very important feature of a cloud which makes droplets grow fast and makes it rain. So like here I've shown some, green is one level of vorticity and yellow is another level of vorticity. It's not me who's shown it, but Jason and Shamriddhi here, who is the moderator today. They've done this simulation of vorticity in a flow, and when there is turbulent flow like this, droplets can grow very, very fast, and that's the logic we're going to talk about. So here this is just a teacup to show you that you need turbulence is good. Like if you don't mix your sugar in, you can wait for months to drink sweet tea, by which time your tea will go bad. So here is one of those vortices that we saw in the previous slide. So if I take one of these vortices and I make a cut through it and I look at it in 2D, I make this cut and I look at it in 2D. That's what we're doing here. And we put droplets here. We're just showing that, this vorticity is going to centrifuge out these droplets, never mind what the red and green are. And this centrifugation is going to make them coalesce and make big droplets. So you'll soon see big droplets in navy blue color when you see this movie. So the droplets are being centrifuged out of these vortices, which are there in turbulence everywhere. And as they go out, they're growing. So you can see some droplets have grown to quite a bit of their, like double or triple their original size. And so this starts out the process of, bigger droplets. And here is a simulation again of Jason and Shamriddhi, which shows, how droplets leave the regions of vorticity in a turbulence, and they agglomerate in the regions between the vorticity. And in these regions, you get lots and lots of droplets. So their chance of colliding and coalescing becomes much more. So the basic idea is that the coalescence is increased much more by turbulence. So we will talk in the next, 10 minutes or so, we will talk about why is this problem so hard to solve? And I'll just give you a basic idea of why it's so hard to solve and then go ahead. But meanwhile, Shamriddhi, do you want me to answer a couple of questions?
Rama, I think we can take them at the end.
Okay.
I'm keeping an eye on them, but those are specific to entrainment, but we can take them at the end.
Okay, we'll do that.
Disturb your flow. Yeah.
Okay. So basically, I want to give an idea here about why this problem is so hard to solve. Like when we have such powerful computers, we have, lakhs of computers running in parallel. Why not? And we know the equations, by the way. We know all the equations that are there to do with cloud formation. So why can't we just solve them? And the next few minutes will be explaining why it's difficult, why we can't solve them, why we can't solve this problem directly. And there are lots of, little things that people can solve. They can make assumptions, make horrifyingly gross assumptions and get some features out correctly. We can't go into all those details, but the message is they're still hard to solve. And there's so many open questions for young people to do their PhDs in. If people want to do their PhDs on cloud formation, cloud aggregation, there's like lifetimes of research waiting to be done. We talked about how aerosols, give rise to the initial part of raindrop growth, and turbulence acts on the raindrops to make them grow more. And turbulence also pushes around the light and heavy portions of the fluid. Remember that as the raindrop grows by condensation, it leaves out a lot of latent heat. So temperature is very inhomogeneously distributed, very randomly distributed in the cloud. And so light portions rise, heavy portions fall. So locally you create vorticity just by, the temperature being not the same. Whoever comes close to the edge of the cloud can evaporate, and that can affect cloud formation. And all of this we're talking about, aerosols which are 1 micron big, and then there's clouds which are kilometers big, and then they aggregate on a planetary scale. So if you look at the globe, I wish I'd brought a movie of the globe, you'll see that a lot of the globe is covered by clouds every day, and there's clouds which are very big, like basically planet scale, 10,000 kilometers big. And all of this physics is mediated by all of these things, which I won't read out. So the range of scales is a mind-boggling 13 orders of magnitude. That gives you one idea, like apart from the complicated physics that's going on, and so many different pieces of physics that are tied in together, it's the length scale ratio that makes it very, very, very hard to compute or solve. So I told you we know the equations. I'll just go over this. Basically, we have Newton's laws in the form of Navier-Stokes equations. They are forced by temperature. And we made huge assumptions about the droplets. We're not even going into that. We know the temperature balance equation. We know the water vapor balance. And each droplet's motion will actually need to be solved for. Like it's getting pushed around by the turbulence. It's falling under gravity. It's dashing with another droplet and coalescing. Heating and cooling is going on. And as the droplets grow, they may not be spherical. And they may actually have very funny shapes. And so how do you solve all this? We've used Megha 5, which I told you is the software developed by Ravichandran and others to solve this. Now, if we want to solve this, these are all differential equations, very complicated partial differential equations. And normally to solve a partial differential equation on the computer, you will write it in the form of difference equations. I won't go into that, but you will write it in the form of difference equations. In the background here, you will see that vorticity picture we had seen earlier. So now we will make tiny, and this vorticity picture was from a tiny part of this cloud. And inside this tiny part, we'll make like this thing called a grid. We will divide it into teeny little cubes. Oops. We'll divide it into teeny little cubes, and we will solve for, the velocity, temperature, water vapor, liquid water, everything inside every one of these little squares by solving those differential equations. And obviously, if I'm going to divide, and the smallest vortex is a millimeter big. So like if I'm going to divide it, I'll get 10 to the power 10, grids on one side. And then that's a cube. So it will be 10 to the power 30. And inside every centimeter cube, there are 1,000 droplets. I have to solve for each droplet. So imagine I make this flow scale grid, which is 10 to the power 30. And then I make this droplet scale grid to understand everything about the droplet motion. And then and these are very, very small. They're 1 micron. These grids are 1 millimeter. So I'm putting a micron sized grid into a millimeter scale object, thousands of them. And then in each little blob, I have thousands. You can imagine that this is impossible to solve. Actually, like no computer on earth can solve, anything. Like they can basically solve 1 meter cube of cloud, and not even in that, they can't solve all the droplets properly resolved. They'll solve the droplets in a very, they'll solve the droplets with many assumptions made. So this is impossible by present day computers. So it tells you like why this problem is hard. But all hope is not lost. We can make some assumptions, and we can solve some small portions of the cloud, and we can solve large portions with big assumptions. So even in this small portion of the cloud, we've solved with these equations. And what we show here is that up to now, I told you that the particles are very, very small. They, they move through the vorticity, And actually, because the flow is very dilute, you won't expect the particles to affect the flow. You'll expect the flow to affect the particles. But in droplet laden flow, life is different because temperatures change due to latent heat. And then like the small scale vorticity gets formed. So this kind of turbulence looks more powerful than plain turbulence. So cloud turbulence is different in the sense that these tiny droplets who are just 10 microns can actually create vorticity, which are, millimeters in size. They're creating these big vortices, although they look powerless. And here's just a picture of a mammatus cloud, which you can see in some places. And here is a new cloud. Read about it in the Cloud Atlas. They're called asperitas clouds. They're recently identified as a new cloud. And we can do simulations from Mega to understand how mammatus or these bulbous clouds form. It's not to go into the story behind it, but just to show a picture. So before I end, I want to, show you pictures of all my former PhD students. Like this is the first bunch and this is the more recent bunch. And like these are the people with whom I've learned a lot. In fact, I showed you the simulations by Ravichandran. I've learned a lot from all of them. Many of them have done work which had nothing to do with clouds, but it's been a pleasure working with all of them. And because I've worked with these people, I get the opportunity, kind of opportunity that I got today, which the organizers were kind enough to invite, where I can talk about my work or their work to you all. And this is my present group. And I conclude by saying cloud flows need to be studied further. So that's the end of my talk. Shamriddhi, I'm ready to take questions.
Thank you very much, Rama. It's virtual, but I'm sure, we can all hear the applause in our heads. So Rama, there are quite a few questions. So I'll begin with the toughest one, I think. And this comes from Prateep Das, if I've got the name right. And Prateep Das asks, what is the main cause of monsoon in India?
Okay.
So I thought I'll give you the tough one.
Okay. So I can give some very hand-waving answer, like the monsoon is an open problem which we're trying to understand. A very zeroth order answer would be as follows. So imagine the earth, okay? Can you see my hands?
Yes, both on YouTube and here. Yeah.
Okay. Here is the earth and here is the equator. Okay, so when the sun shines directly on the equator, what's going to happen is the equatorial regions are going to be hotter than the rest of the world. And because they're hotter, the air is going to rise, which means it's going to go radially outwards from the equator. So when the air rises at the ground level on the equator, because the earth ground is the hottest, you will have air rushing in from the poles, the other part of the earth. It's going to rush into the equator, and what you have is something called a convergence. And because this air is converging and rising, anytime there's convergence and rising, it's going to take water vapor up with it. And whenever there's water vapor up, there's cloud formation and rainfall. So this is a general thing about why, like there's lots of rain on the equator. But as the seasons proceed, the sunniest part goes up and down to the tropics. So like the cloud band moves up and down. So a zeroth order explanation is that when the cloud band moves a little up, you get some chance of rain over India. But that doesn't answer the question, because you can say, why doesn't it rain by the same logic over Arabia? And because Arabia is at the same latitude, why are their desert and we getting heavy rain at the same time? So there's like many different things which happen. Part of the reason is that we have the Himalayas. Part of the reason is Bay of Bengal and the Arabian Sea. So all of these things come in extremely complicated ways which are not yet understood. So the zeroth order explanation is the movement of the cloud band.
Okay, so there is another question. What is cloud fluid? Explain its formation. I suspect this was roughly sent at the time when you were talking about what comprises a cloud in terms of air, a little bit of water vapor, etc. I
So
think
they're
that's
asking
the
what is
context.
cloud fluid?
Cloud fluid, yeah. I think that's the context
Okay.
from the
Okay,
time.
so like, from here, it looks like this very innocent puffy ball, like it almost looks like a powder puff, which you can, use on your face. But when you go in there, we've seen that it's violently turbulent. So a cloud fluid, I mean, that portion of the air is just violently turbulent because of, some movement, some potential energy being converted to kinetic and so on. So now when you fly through it, in a plane, you will see that it's very dilute actually. So you can't really see each individual water droplet, but on the whole, you see you see that there is some moisture there. So we've been taught that the color we see is just, water droplets, scattering off light. So basically, it's mostly air, vast proportion of air, 1 gram per meter cube of water vapor, water, everything together, and a few aerosol particles. I mean, very large number, but very, very small in volume fraction. And that's it, and turbulence.
Okay, great. So the next question is related to aerosols. It comes from Vineet. And Vineet asks, what if anthropogenic aerosols are not emitted? And will it affect cloud formation? So I think his question, what if they're not emitted, anthropogenic aerosols?
Okay, that's a very, very beautiful question. First of all, there's lots and lots and lots of natural aerosols in the world, okay, in the Earth's atmosphere. So sea salt aerosol is a very, very important aerosol. So every time there's a wave breaking or, there's turbulence on the surface of the ocean, spray comes out. And when this spray evaporates, you get tiny, tiny, tiny particles of sea salt, which can get convected upwards every time there's a convection. And once they go up, their terminal velocity is so very small that they're going to take many days to rain back down. So all the time there's creation of sea salt aerosol. There's also dust, and from desert there's dust particles, there's volcanic ash, there's lots and lots and lots of natural aerosol. So rain can happen without us guys. Rain did happen before we guys started polluting and messing up the atmosphere. They don't need man-made aerosol. Man-made aerosol can actually change the story. It can come and mess up the story. For example, like if you have a city which is very, very polluted, and above that city, when clouds form, what happens is, because the number of aerosol particles is so much more than elsewhere, than in a cleaner environment, you'll get lots and lots and lots and lots of tiny droplets forming. But because the water vapor that was there is shared between many, many more aerosol particles, you will get much smaller droplets. So you'll get more droplets, but smaller droplets. So it's harder for rain to form when, you're starting out with even smaller droplets than before. So this is one way in which man-made aerosol messes up the answer, but it does other things as well. Its full effects are not very clearly understood.
Thanks. So there's a question from Pankaj Rana. And Pankaj Rana asks, is it possible to understand the turbulent flow using Boltzmann equation of dilute gas?
Okay. So the thing is that the easiest equation to use in this context is, is the Navier-Stokes equations. And Boltzmann equation can be used, but if you use Boltzmann equation, see, Boltzmann equation is written for situations where the mean free path between molecules is very, very large. So like in the limit of, in the limit where the mean free path between molecules, we're talking molecules, not water droplets, is very small, the Boltzmann equation will technically reduced to the Navier-Stokes equation. So yes, you can use the Boltzmann equation to solve it, but the Navier-Stokes equation would be more convenient and better in this context.
Okay, thanks. So there's a question from Akash Simha. I think Akash also has a follow-up question later, but on something else. So I'll just ask this one now and then address the other question later. So Akash Simha asks, could you give some hints on how to do the calculation? And within brackets, Rama, Akash mentions, you said it needs 12 standard knowledge, which describes the limit on the size of a cloud droplet.
Okay.
So this was when you remember the context, right, Rama?
Yeah,
So
yeah.
this was asking the context of condensation.
Was it this one?
Yeah.
Okay, let me go there. So like basically what you need to do is the following. You have this simple equation which I had written somewhere. Yeah, here it is.
You have it there. Yeah.
So like basically there is this thing called the Clausius-Clapeyron equation, which says that the rate of condensation is proportional to the supersaturation. So like suppose the saturation vapor pressure is S, then suppose saturation vapor pressure is 1, I've divided out by the saturation vapor pressure. The amount of water vapor which is above saturation in the air, that much can condense out. Okay, and the rate of this is A is the radius of a droplet, and so A times dA by dt is some constant times supersaturation minus 1. So you can, if you know the supersaturation, if you know how much water vapor there is and what the temperature is, you can calculate the supersaturation, and by Clausius-Clapeyron you can derive this equation, and you can see how the radius A changes with time, grows with time or shrinks with time. It could evaporate or grow. Like here I wrote evaporation because this is for a drop which has fallen out of the cloud. So like I know the radius of my droplet by knowing the supersaturation and the temperature. Take that radius and put it here and make a force balance. So suppose it's a teeny radius, then it is in Stokes flow, this droplet. Its weight, its reduced weight is going downwards, not just its weight. I should have said its weight minus the weight of the volume of the fluid which is displaced, the Archimedes one. So there is a buoyant force going upwards and a drag force going upwards. And in 12th standard or IIT preparation, you'd have surely studied for a Stokes flow that the drag is equal to 6 pi times the viscosity times the radius times the velocity. So you can write a little force balance equation for this and solve it. So you can actually solve with 12th standard stuff how it's coming down and how it's growing as it comes down. So then you can have it crashing against other smaller droplets, and you can have them coalescing, and then you have a bigger drop which then falls faster and all of that. So does this give an idea to the person who asked on how to solve this?
I hope so.
Okay.
And if there are any class 12 students, exercise, right? for the exam.
Sorry?
I said, if there are any class 12 students in the audience, even if your exams are postponed, that's an exercise to go ahead and do, right?
Yeah. I mean, these things become harder for the rest of us to do. It's easier for the younger ones to do.
Absolutely. I agree. So,
yeah. Like
Rama,
this reminds me of that Tom Lehrer song, like about new math. So if you guys haven't heard that song, you should go home and listen. It says like new math is so simple, so very simple that only a child can do it. Yeah.
Okay, so now there are harder questions. So Vineet Rama asks, is there any role of jet streams in the formation of clouds?
Of the jet stream, like he means the one in the Atlantic and the Pacific.
I was actually confused because is it the Atlantic? I mean, Vineet, if you could clarify, or is it in relation to something he's using for your entrainment picture? Shall we go with Atlantic? But maybe that's for more global circulation, right?
Yeah, so the point is that any circulation in the ocean has an effect on cloud formation, because any circulation determines evaporation. And so for example, we know that El Nino, oops, I'm so sorry. I'm so sorry about this. We know that, the El Nino affects the Indian monsoon, and that's pretty well known, although by how much and whatever is less well known. So yeah, any kind of ocean circulation can affect the monsoon, affect cloud formation. So for example, if one place in the ocean becomes ever so slightly warmer than another place, then the air can go in that direction, rush in that direction. And if that air is moisture carrying, it can divert the cloud formation to another place. So many of these things can happen. So yes, everything affects everything. It's a horribly complex problem.
So actually, what I was trying to second guess. So Govindan Kutti's question is regarding that. So Govindan asks regarding the reduced entrainment of ambient air inside the cloud. So that's the context. Could this be because of the difference in density of moisture air inside the cloud and dry air outside?
The entrainment.
The reduced entrainment of ambient air. So okay, is it an issue of the contrast between density of moisture and dry air?
Okay. This is a very, very nice question, and it's a very nice first guess. So I should compliment you on asking this question. The thing is that if you take like a jet, which is the same temperature as its ambient, then it will entrain a certain amount of air. And now if you have a hot jet, so for example, rocket effluents, when a rocket takes off, there also you see that angle increasing. And as the angle increases, it means that it's entraining more. So like, unfortunately, like when it becomes hotter, yes, you're right, it affects the entrainment, but it actually increases the entrainment. But you had a very good guess in this, that in the cloud, what's different is that heating happens along the way, not at the starting point. Like in a rocket smoke, like heating would happen here, whereas in the cloud, heating happens along the way because of condensation and latent heat, and that seems to shut off the entrainment. So it has something to do with heat injection, but it's not directly density, because if it was just density, then even a rocket thing or a hot thing coming out of a volcano should not be entraining, and those things entrain much worse than cold jets. So like cold jets entrain some, hot jets entrain a huge amount, and clouds seem to entrain much less.
Great. So now we have a question from Abhijit Singh. By the way, all of you, do pardon me if I get your names a little wrong. So I beg your forgiveness. So Abhijit Singh asks, we know that there are a lot of electrical phenomenon going on inside a cloud. Is it, so I think that's a question mark, full stop there. So is it safe to neglect all of them? For example, static charges, I'm just paraphrasing the question, do they have anything to do with rain formation?
Yeah, so yes, they do have things to do with rain formation. And in particular, like we don't understand lightning, which forms due to charge separation in clouds. So the one word answer is yes, they can affect many things, and we don't know how. And one thing that can happen is that, when there are charged particles in the very upper cloud, it can even, affect the formation of ice particles. So yes, they affect many things. And we don't know exactly what they do.
Wait, so Akash Sima, who had a question before Rama, Akash has a follow-up question, which is, are the simulations you showed for the droplets going away from the vortices and coalescing in 2D or 3D? It's 2D, I guess. I think it's Jason's simulations or Cruz, the simulations showing droplets going away from the vortices and coalescing. So just Akash wants to know whether it's in 2D or 3D. So I mean 3D, whether you projected
Okay,
in
these
ITM.
particular simulations are in 2D, but we've done exactly the same work in 3D as well. In fact, like me and Shamridhi and a few students, Lokahit, Agastya, and Jason, and Kroor, who's Ravichandran, we've all collaborated and we've asked what happens if this vortex is in 3D, and we have tried to answer that question. So like, yeah, the same thing will happen in 3D as well. That's our belief. But we haven't done like very elaborate 3D cloud simulations. We're in the process of doing them to see whether all of these precise effects happen in the precise way that we're talking about.
Okay, so Abhijit Singh has another question, and it's the following.
One more thing, the mega simulations are all in 3D.
Right. Yeah.
Okay. Huh.
Right. So Abhijit Singh has another question, which is if aerosols help cloud formation, is there a correlation between pollution and cloud density? Part of it you answered when you were talking about anthropogenic aerosols. Yeah.
Yeah. So yes, there is a correlation, and there are actually like, field observations. Actually, people in IITM Pune, for example, they fly through the cloud, especially they fly through polluted clouds and they fly through clean clouds, and they try to study the difference. And such experiments have been carried out in many parts of the world. And one consensus, as I said, seems to be that there are many more smaller droplets in a polluted cloud as opposed to in a non-polluted one.
So we shouldn't make pollution great again, right, Rama? So, okay, so Anshuman Das has a question, okay, probably related to pollution. So the question is, what about turbulence in acid rain formation? What have they done to the rains?
What about turbulence in acid rain?
Yeah, what about turbulence in acid rain formation?
Okay, so basically acid rain will happen if the aerosols and things that you're forming the droplets on are themselves polluted, are themselves poisonous. So then you get acid rain. So that whether the aerosol particles are the terrible variety or the harmless variety like sea salt, you're going to get the same kind of turbulence. I don't immediately see why turbulence should be different because, the aerosol particles are made of a different material.
Right. So Abhijit has another question, but this might be a little, away from this. So, but I'll read it out nevertheless. So Abhijit says that Abhijit has been recently, so I'm paraphrasing it, it's a bit long, recently reading a chapter on atmospheric electricity in Feynman's lectures, volume 2, chapter 9, and found Feynman's argument very sketchy and refers to a lot of phenomena whose mechanisms were yet to be figured out when he gave that lecture. So Abhijit asked that in case you have read or remember the lecture by any chance, how much progress has been made since then?
Sorry, I don't know that lecture. So I don't know, I can't answer your question. But I can tell you that, charge separation in a cloud and lightning formation are open questions. They're not clearly understood. All we know is that charge separation keeps building up and up. Like I've even forgotten whether the positives are on top or the negatives are on top. But then like when it reaches a certain level, then it discharges. But what causes the charge separation in such a massive way in the first place is not understood.
And you also referred to the issue of static charges, etc., for ice crystals in a previous
for ice
question.
cubes and all, it's very important.
So Kiran Mehta wants to know, is anybody in the world studying astrophysical clouds, as for example, exosolar systems under formation, star-forming clouds, etc.? I see Ajit Pallavi and all of you in the audience. So, Rama, go ahead and they could unmute themselves, but Rama, go ahead first.
Yeah, they can answer it a lot better, and I'm very sure that people are studying them.
Right. So I'll pause for a second in case they would like to. If not, I'll go to the next question. They can interrupt me when they want. So I'll go to the next question.
Pallavi, do you want to answer this?
in the Nope. So let's move to the next question, Rama. So this comes from our friend, I suspect, Sujit from IITM. So Sujit asks, what causes cloud bursts?
Okay, so in fact, like I have a few papers on cloudbursts which I've collected day before yesterday and I haven't read. So, but basically what happens is that when you have an enormous collection, very, very rapid formation of very large drops, then you get a cloudburst. So effectively, you need some violent convection which is moving upwards. So like basically you have from the earth a very large amount of water which is rising like with high speed, and somehow it doesn't lose its water vapor, it loses its water vapor much less, and it reaches this height very fast and extremely quickly. Let's say the aerosols are in the right number density to form really, really big drops, and it's turbulent enough that this can happen. So cloud bursts very often form close to big tall mountains where the air is risen up, and then you suddenly have a huge amount of rainfall which has gathered itself in no time. So this is the zeroth order thing I can tell you, Sujit, but I'll have to read more papers to answer it exactly. But people have studied it in greater detail than this.
Great. So the next question comes from Quasar Supernova. I suspect that's not the real name. And the question is, how accurate are theoretical models in the field compared to actual observations? There's a follow-up question. Is the Navier-Stokes equation really fully correct? There's another question, Navier-Stokes, which I'll ask later.
So what's the second part of the question? Is the Navier-Stokes equation
really fully correct? But you can couple that to another question, Navier-Stokes, which I'll ask later. So the first question is, how accurate are theoretical models in the field compared to actual observations?
Okay. So it depends on what kind of thing we're asking. So like we talked about this 10 to the power of 30 grid points, which no computer on earth can solve, right? So like all theoretical or computational answers are made in this way. So you have basically what you need in a cloud, which is not yet done, is solve the full Navier-Stokes in a very small portion of the cloud, then do these simulations which are called large eddy simulations. In the large eddy simulations, you solve only for the big eddies. So you make grids which are really big, and then you don't solve for the details of the turbulence, but the small scale turbulence, you give the correct forcing for a cloud. So you know that these systems are very, very non-linear. So like what a big scale does will get affected by the small scale, and what a small scale does will get affected by the big scale. So if I just solve for the big scales and ignore the small scales, I'll be making a terrible mistake. So I'll have to model what the small scales do and feed it into these large eddy simulations. That's step one. Step two is take these large eddy simulations with big grids, and they can still be just about a kilometer in size. Whereas we want to ask questions, if I want to observe clouds, I want to check which is a rain cloud, what is going to happen, and connect it to my calculations. I have to solve global models, which are on much, much, much bigger scale, not kilometer scale. So the large eddy simulations have to feed into those. So we need like this 3-step procedure to solve the thing. I think people are just beginning to think of things like this. So like the big models, nowadays, the way the big models run is they don't have good backup simulations. They run with lots of, handmade parameters put into them, empirical parameters. So because they run with empirical parameters, they are fit to one kind of observation, and they're reasonably good for predicting that kind of observation. And more people are using machine learning and things in this process, so they can predict that kind of observation well. But the summary is that the Indian monsoon is so complicated due to so many reasons that none of these calculations can predict it well, which is why, every year we have a tension. We just don't know when the break periods are going to be, whether it's going to be an average rainfall year, We don't know any of these things. So clearly, like calculations have a very, very long way to go.
Okay, so there's a question from our friend Parul, I suspect. So Parul asks, you had shown different shapes of clouds. Are there some that produce more rain as compared to others, depending on their shape?
Okay, so cloud shapes get set by a variety of things. Like, for example, Professor Narasimha, whose simulations I referred to and who passed away in December, sadly, he actually was quite a magician at designing cloud shapes. So he could actually make this cloud in a lab, where basically he was making a cloud by warming up a portion of the fluid as compared to the rest of the fluid. And he could change this warming up process in a very clever way. So he had, slight acidic fluid, and he would have electrodes with electricity passing through. So they would selectively warm up selective portions of the jet as it went up. And then he could create clouds of different shapes just by playing with those electrodes and the amount of heating he was giving. So like this, the kind of shape you can have does have to do with the kind of heating and the kind of condensation that's going on. So like if you back out, if you do some thought experiment on this, you see that because the kind of heating changes the shape, and the kind of heating in a real cloud doesn't come from Narasimha playing God, but it comes from water droplets which are condensing and things like that. So you know that the kind of water droplets that have been created has something to do with the shape, although nobody knows what the connection is. Nobody at all knows what the connection is. So yes, they have to have something to do with each other, but we don't know what it is. What happens is that once a cloud is formed, there's planetary scale aggregation of all clouds. Like clouds all collect and lots of other things happen apart from just the shape. So then it becomes very, very difficult on a planetary scale to give an answer to these things.
Thanks, Rama. I shared for everyone some of the videos from Narasimha's group on what you were talking about.
Very nice.
Okay, so that's okay. So there's a question from Nazneen Sharif. Does celestial events, such as an eclipse, planets coming close, have an influence on cloud formation and formation of turbulence?
So again, like this is a question for the astrophysicists, but like on the whole, we can say that disturbances within the Earth are a way bigger factor, and we can neglect what is happening from outside the Earth's atmosphere for the most part. So I would say they will have a negligible effect.
Okay, so there's
but I can be corrected by astrophysicists.
So there's a question by Sachidananda. Sachidananda asks, and this sort of couples, Rama, with the earlier question, the second part, which was, is the Navier-Stokes equation really fully correct? So Sachidananda asks, any idea on how close people are to solving Navier-Stokes equations exactly? So I'll let you be the judge of exactness, Rama, and answer this.
Okay. So first, let's answer the second part. Let's say that the Navier-Stokes equations are God's own truth, and can you solve them exactly? Yes, there's a variety of situations in which Navier-Stokes equations can be solved exactly, especially in laminar flow. If it's laminar flow or simple unsteady laminar flow, they can be solved absolutely. I mean, like you can solve it, somebody else can solve it, and everybody can get the exact same answer in space and time. Everywhere you can get the same velocity, same everything. Now, when you come to turbulence, you know that turbulence is a chaotic process. It's a very brilliant example of a chaotic process. And chaotic processes are well known for being very, 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 very sensitive to initial conditions. So like any tiny error you make in the initial condition. So suppose like the temperature on a given day is 30.00000000001 and you take it as 30 and you solve this. Like even if you have the world's best computer which is solving everything exactly, at some point your trajectory will diverge away from the 30.000 thing. So nonlinear processes are extremely sensitive to initial conditions. So to get exact answers in space and time is impossible. However, you can get average properties very well. So you can get, basic properties extremely well if you can solve it exactly. But as we discussed, for higher Reynolds numbers, there's more and more and more grids needed, and we cannot put in so many grids. So we can only solve for low Reynolds number flows, not cloud, with some degree of exactness. So the Navier-Stokes equation, even if it was God's truth, this is the limitation in solving it. Now, is the Navier-Stokes equation the correct equation? So like it's for these kinds of situations, yes, the Navier-Stokes equation is pretty correct. The reason is that whenever you have a continuum, namely you have many, many, many molecules in every small blob that you're considering, and a small blob consisting of an extremely large number of molecules is doing a certain kind of behavior. In this scenario, you write Newton's laws pretty exactly for this blob of fluid, and you can get answers. You've made additional assumptions in the Navier-Stokes, which is that the flow is incompressible. You can actually, if you want, release that assumption and write down the correct equations for compressible flow. You can also recognize that things like viscosity can be a function of temperature, pressure, and other things, and write additional things like, although in most of the time when you write Navier-Stokes, you take viscosity to be a constant. So under these situations where viscosity is reasonably constant, where the flow is reasonably incompressible, like in any of these flows where typical speeds are much less than the speed of sound, you can make that assumption with pretty good accuracy. And then like in all of these situations, you're doing great with Navier-Stokes. But like, for example, if you're trying to solve, a rocket with containing human beings is trying to come back to Earth from outer space. And if you solve Navier-Stokes equation far away in the atmosphere where, molecules are very, very far apart and you cannot assume continuum, then you'll go very wrong.
Oh, sorry, I was on mute. Sorry, Rama. So now we I think this is the last question, and we are really pushing our luck. We are pushing you into the Bermuda Triangle. So the question comes from Pushpraj Bhardwaj. And Pushpraj asks, because there was a, any arguments, so the question is, any arguments regarding the cloud formation in the region of Bermuda Triangle? And then there's a sort of rationale to the question, which is, Pushpraj adds, because there was a theory to explain the mystery of Bermuda Triangle by telling that very low pressure regions develop and winds are so high. So Rama?
I actually don't know the answer to this one at all. I don't know the answer to this one at all. But we know that, wherever there's low pressures.
But in general, yeah, you could probably comment a little on the low pressure.
I think the person asking the question also knows this, but yeah, I can't answer about the Bermuda Triangle. But thanks for asking the question. I'll read it up.
Right. So let me again just check, Rama. Give me a second. I'll again check the YouTube page. Yeah, I think I have sort of asked all the questions that were raised. So again, Rama, thank you very much. I speak on behalf of the Cosmic Zoom team, this wonderful online exhibition curated by Ajit and his team of very hardworking colleagues, students. Anupam is there, Bertie is there, the whole sort of team of people working on this. So I thank you on behalf of them, on behalf of everyone who was listening to the talk. So thanks again for your time and for sort of taking all the questions. So, Anupam, should I hand it over to you?
Yeah, I could step in.
Yeah,
Hi, thank you.
okay, Bertie.
Bertie or Ajit
Yeah.
or whoever.
This is Bertie here. Thank you all for being part of this, and a special shout out to Professor Rama Govindarajan for being an absolutely fantastic lecture. Thank you, ma'am. Thank you so much. And it also,
That's for the opportunity to all of you.
I am in Dulles Colony, and it's rained here after a long time, and I can smell the petrichor. So it was really interesting to listen to the talk while smelling the petrichor. So thank you so much. Special shout out to Professor Samriddhi for being fantastic moderator. Thank you, sir, and thank you to all the amazing participants who have sent in really nice questions on chat as well as on YouTube. As the professor pointed out, please check out cosmic-zone.in. All the events are coming up. There are only a few events left, but they're really interesting ones. Tomorrow, Professor Sanjay Jain from the University of Delhi is talking about life, its origin and place in the universe at 7 p.m., followed by Professor Axel Brockman from NCBS, who will talk about the interesting life of the giant honeybee. And on Saturday, I'll be talking to ecologist Dipani Sutaria about dolphins and humpback whales at the Arabian Sea. So these are the events that are coming up. And every day in the morning at 10:30 a.m., we are having mediator guided tours of the website. It's all free. Do check in. It's a lot of fun, a lot of engaging things. If you have any classes like in schools and colleges would be interested, please do tell us and we'll be happy to take you through. And all that remains for me to say is thank you for being there. Thank you for spending the evening with us. A special thanks to Professor Samriddhi and Professor Rama for joining us. And these videos will be up on the website soon, so please keep a lookout. Thank you to ICTS and to the AV team for doing this. So that's it. Have a good evening, and we will end the call now. Thank you.
Thank you.
Thank you. Thank you. Thank you, Rama and Samriddhi.
Thanks.
AV team, you can stop the live stream.
Yes, sir.
Professors, please feel free to leave the meeting. Thank you all. Have a good evening.
Bye.
Bertie?
Yes.
So I'll stop.
Gopi.
Yeah.
Yes, Gopi, you can stop it. Thank you. Bye.
Bye. Bertie?
Yes, yes, Gopi.
Can you send your contact number?
Yeah, I'm messaging it to you right now.
Yeah.